talk is about computable centering methods for spiraling algorithms and their duals with motivations from the theory of Lupno functions. And this quote is from Hong Kong Polytechnic University. Please go ahead, Scott.
Thank you for the introduction. And yeah, it's a long name. I will try to make it worth it for you. Let me start out by apologizing to the other people in my session for missing their talks. I look forward to watching the replay, but in order to get a more stable internet for giving this talk, I decided to take the 6:20 a.m. ferry to come into PolyU so that I could use my office internet rather than the internet on my island. But the talks look really interesting, so I'll check them out on the replay. And I'll just dive right in here. And I'll start by showing you the obligatory slide that we always start optimization talks with, which is a slide that tells you I want to minimize a sum of two functions. These functions are connected through some kind of a linear equality. And there might be other constraints on this as well. And as this is an optimization conference, I don't need to spend too much time introducing the concept of a splitting method. Most of you would be familiar with splitting methods. They're methods that allow us to decouple constraints that are hard to simultaneously satisfy or separate out minimization steps. So kind of a standard example of this is a projected gradient algorithm where you follow gradient descent and then project onto your constraints. And then another sort of variant that we've all seen and are familiar with is alternating projections. And I'm going to spend most of this talk hanging out in the Cinderella applet for a couple of reasons. One is just that I think it's nice to do something different because it is, an online conference and everyone's stuck in front of their computers anyway. And the other reason I'll be mostly sticking within this applet is I want to give you kind of concrete examples. But I would like to emphasize that while I'm going to show you a lot of feasibility problems, the goal of this talk today is to talk about a more general optimization framework and developing a more general optimization algorithm beyond this more narrow scope of feasibility. And so we will get there. We'll get there about halfway through, but it'll help to start with some concrete things. So alternating projections, of course, you project onto one set, project onto the other, project, and continue until you make your way into that feasible point there where our two constraint sets, this line and this circle, intersect. And of course, there are more exotic ways of doing this. This is an example of something called the proximal point algorithm. And here's another algorithm from that same family. This is called the Douglas-Ratchford method. And as I give this talk, you'll be seeing these little citations pop up in various places. And those are just articles you can look at if you want more information on what's on any of these slides. And there is a complete slideshow as well if you prefer that to watching me drag things around here. But the construction of this is you start with a point, project onto the first set and go twice as far, which we call a reflection. Then you play the same game with the second set, project, go twice as far, which we call a reflection, and then you average with where you started. So at each step of this construction, you build yourself a triangle. And so here's the next step. I reflect, and then I reflect, and then I average, and I keep playing the same game, building this triangle over and over. And eventually I will spiral my way in towards this feasible point here. And the first people to take a look at this really kind of highly structured example of a circle and line were Braley Sims and John Borwein. And they did something kind of neat, which is using this tool, Cinderella. Why don't I turn that back off? Using this tool, Cinderella, they plotted a grid of points, rainbow colored grid of points here in the plane. And then they looked at where those points were set under various numbers of iterates. Oops, need to drag that back. There we go. So here we are at 0 iterates. There's our plane of points. Let me just drag this so you can see the citation. And then here we are after 1 iterate, a few more iterates, all the way up to 9 or 10 iterates here. And you can convince yourself that this plane of starting points, their destinations are sort of slowly swirling and making their way in here towards this feasible point. Move that way over there. And this convergence, they conjectured it was global. And John did a nice little article with Fran Aragon where they showed that given some assumptions, you could show that this was global. And then this was finally resolved by this fellow here, Joel Benoit, who built this Lyapunov function that I'm showing you here. And you could think of a Lyapunov function as a function that just sort of tells you the energy in the system at a given point. And so it's going to be 0 at a fixed point, and it's going to be bigger when we have more movement of our sequences. And he designed this Lyapunov function here to have this characterization that at each update, the difference vector, this vector between subsequent iterates, comes in at a tangent to these level curves. And in Rn, there's sort of a dot product characterization here. And so you can see as we play along, we slowly spiral our way in. And then Min Dao and Matt Tam, who are both presented or presenting at this conference, they extended this to more general kinds of feasibility problems with more general graphs of functions and finding roots of more general functions. And so both of these articles are sort of influential in what we'll be looking at today. And in particular, this property of this tangency of these difference vectors is very interesting to us. And there's something else that can go along with this spiraling characterization. This spiraling has been observed in a number of contexts, not just feasibility, but also more general optimization contexts. And I'm going to show you something that we often observe with it, which is, as I'm going to plot here for you, the changes horizontally from one iterate to another in this spiral. And that horizontal change is actually what we would call the change in the shadow sequence of projections onto this horizontal line, right? The horizontal change from one iterate to the next, that's the same as the differences in these projections. And you'll notice something, which is that as I come around the top of the spiral, there's more change from iterate to iterate. But when I reach the sides of the spiral, I'm mostly going up and down. There's not a whole lot of left-right going on out here at the sides of the spiral. And so I hit a little valley in terms of my change from iterate to iterate. But then as I make my way around the bottom of the spiral, there's more change from iterate to iterate horizontally. And so I have a little peak. And then when I reach the side of the spiral again, there's a little valley. And at the top of the spiral, there's a peak, at the side a valley, at the bottom a peak, at the side a valley, and so on and so forth. And so I get this very beautiful sort of aqueduct kind of pattern of peaks and valleys. And when I see that, what I'm thinking to myself is, in some sort of lower dimensional subspace, like this line, for example, I'm thinking that this shadow sequence is wobbling back and forth because the true sequence, this red sequence that I've plotted here, is spiraling. So that's what I'm thinking. And the goal of this talk is going to be to ask, how can we get to the center of this spiral a lot faster without wasting so much time going around in loops? And I'll show you one way of doing that, which is something called the circumcentering reflection method that was introduced by these folks down here. And to understand how this works, you'll need to understand what a circumcenter is, which, if you like old Greek geometry, you're probably already fine here, but if otherwise, I'll introduce you here. It's the center of the circle that contains all three of these points. So it lives on the affine hull of these 3 points, and it's equidistant from all of them. Another way of thinking about this is this purple point, this circumcenter, lives on the intersections of the perpendicular bisectors of the triangle created by these points, A, B, and C. Now, you have to be a little bit careful in actually working with these in computation, because you'll notice if these 3 points are collinear, that circumcenter lies at infinity. So it's something you have to kind of bear in mind, but I won't talk about it much more in this talk, just in the interest of time. I'll focus more on how we use these things. And here's how this has been used for speeding up the Douglas-Ratchford algorithm. So I build my triangle as before. I start here, I reflect, and I've got a triangle now. 2 of my vertices are reflections. 1 of my vertices is a Douglas-Ratchford iterate. And then I just take the circumcenter of this triangle. And as I drag this around here, it probably doesn't take too much work to convince you that circumcenter update will always lie in the line. because the line is the perpendicular bisector of this side of the triangle, isn't it? So it's always going to live there in that line. And after I'm in that line, after I'm living in that line, this thing feels a lot like Newton-Raphson method because I'm starting in this axis, I project onto this curve, and then I follow its tangent back to the axis, right? This is how we teach our Calculus 2 students Newton-Raphson. We don't talk about, oh, you're building a quadratic surrogate for a minimization problem. We just tell them, okay, you follow the tangent of the curve down to the line, right? And find the root. And actually, this characterization is kind of neat. You can use this to prove a sort of interesting property of this thing, which is that it'll actually find the root of the square root function, right? We play the game, we project onto the curve, follow its tangent, project onto the curve, follow its tangent. I'm using these semicircles now because all the points are going to lie in this line. These semicircles to connect one iterate to the next, just so it's readable. And we converge our way in. And in fact, you can prove that this will be eventually superlinear, even for functions like this. So that's something that's shown in this kind of fun article with Neil Dyson and Jeff Hogan. But of course, we're interested in more interesting things than curves and lines, right? We're interested in a more general optimization framework. And in fact, what I would like to do is come up with a way to do something like this in a primal dual sort of setting, where I'm able to compute one algorithm and the dual of that algorithm is spiraling, right? This is a notion that we have in convex optimization, where if I have an algorithm that's solving a problem for one kind of convex function, then I know it has a dual partner living out there in the universe somewhere that is solving a related problem on this, the dual partner function, right? So let me show you an example. So this is called a basis pursuit problem. And our goal is to minimize this one norm whose level curves I have plotted for you here, subject to the constraint that our solution lives in this line. So this is essentially finding a sparse solution to a linear equality. And the algorithm that I'm using is something called ADMM, or alternating direction method of multipliers. And you can see it's doing a fine job of solving this problem. If I twist the line around, you can see it finds the sparse solution up there. And I'll put the line down here. And what I'm going to do for you here, if you're interested in kind of this relationship that I'm going to show you here with these purple dots and these other primal variables, this is a kind of the classical article that connects these. But I'm going to plot for you the differences of these subsequent purple points that are involved in the construction of this direction of multipliers algorithm. And as I plot the difference from one point to the next, you can see we have a valley, a valley, a peak, a valley, a peak, a valley, a peak. And that's interesting to me because these purple points are the shadow sequence for the true dual partner of this alternating direction method of multipliers algorithm. And I just want to be clear here. Often in the literature, people will call these purple points the dual. I'm going to call them the dual shadow, just because I'm thinking of the dual as being Douglas Ratchford, not this shadow sequence of Douglas Ratchford. And because of this peak and valley sort of pattern, I suspect that when I reconstruct these Douglas Ratchford iterates, which I can do, I'm going to see that they are spiraling. And sure enough, they are. And if you want to read a paper that I found very useful for this. This paper by Eckstein and Yao is very nice. But let's zoom in on these red dots, this Douglas Ratchford sequence, and look at this spiral. And it's a definite spiral pattern as far in as I can zoom. And so the kind of naive thing to do is ask what happens if we try to apply the circumcentered reflection method to finding the center of this spiral. The bad news is it doesn't work. Here's why. Let's talk it through. Turn on the labels here. Okay. Oh, there's only one reference for the rest of this talk, and that's my paper that's here on arXiv, where I explain all this stuff. So we have our triangle that we can compute. This is the fourth Douglas Ratchford step, and this is its first reflection, and this is its second reflection. So we get this triangle with these three vertices. Now this reflection over here is not a reflected projection anymore. It's now a more general thing called a reflected proximity operator. We don't need to worry about this point for the sake of this talk. Let's focus on this one over here because this is the one that makes everything go wrong. This is a reflected projection across the unit ball in the max norm, right? So that's lit up in pink. Reflection across this set. And that's a problem. It's a problem because the perpendicular bisector of this side of the triangle here, that perpendicular bisector is now going to contain some exposed face of the unit box, isn't it? And that's a problem because any point that lives in that perpendicular bisector is not likely to be anywhere close to the center of our spiral. In fact, here it is out here. Here's our circumcentered reflection update, this teal point here. And there's our spiral. It's nowhere close. It's not going to help us to get a better solution. And our goal is ultimately to find the center of this spiral, project back onto the unit box, and then pass this update back to our primal variables. That's what makes it kind of a primal dual approach. So since this doesn't work, we're going to need to invent something new. And to invent something new, it helps to be inspired by something old, or rather by two kind of old things, or rather two kind of new things relative to the history of mathematics. So let's take a look back at Joel Benoit's Lyapunov function here, which is similar to the ones built by Mindau and Matam. And let's just put a step of circumcentered reflection method over the top of it. I'll give you a moment here to kind of look at this and see if you can notice the pattern for yourself. It might just jump right off the screen at you. The really cool pattern here is that this step of circumcentered reflection method looks like a step of gradient descent applied to minimizing this Lyapunov function. It looks like a step of gradient descent from 3 points, from here, here, and here, the midpoints of this triangle. So that's kind of interesting. It's really interesting when you stop and just think about the fact that when you're doing this algorithm in general, you don't know the Lyapunov function. Right? You know that one exists, which is something that's inspirational in this case. This is something that was pointed out to me by Bjorn Ruffer at University of Newcastle at a seminar back in December. He's also done research where he and Ohad Galati built Lyapunov functions that had similar characteristics locally for non-convex Douglas-Ratchford iterations. And the point that he made that sort of stuck with me is that essentially, this asymptotic stability guarantees the existence of these things under some assumptions that are explained in a paper by Chris Kellett and Thiel. And so what I would think is anytime I have spiraling, it's not a bad thing. It's not unreasonable to assume that I'm going to have a Lyapunov function that satisfies conditions similar to the conditions that are assumed by Joel Benoit and by Mindau and Matam for their Lyapunov functions. And so if I think that I have these kinds of tangency conditions, I could try to design an algorithm that does something similar here with respect to the Lyapunov function, but without using the reflections. Because remember, the reflections were what caused the problem on the basis pursuit. If I can avoid them, maybe I can get something that will work for that algorithm as well. So here's what I came up with. And this algorithm over here on the right only uses the governing sequence, the spiraling sequence. It doesn't use the reflections. So you could have somebody could give you points out of a black box that are spiraling in a circle, and you could then build this. And the way that I build the triangle is like so. We take the starting point, we reflect across the first update, and that gives us the next vertex of our triangle right over here. And then to build the last vertex of our triangle, we do a slightly more complicated thing, which is we take our starting point and we add on to it 2 copies of this difference vector. And then we just add on 2 copies of this first difference vector projected onto this second difference vector. So that brings us to this point out here that I've called pi t. And as I drag this point around, you should be able to kind of convince yourself that my construction is returning us this solution here that looks like a step of gradient descent from both of these points. But there's something else that's interesting about this, which is that this triangle lives in the affine hull of 3 Douglas-Ratchford iterates. And what that means is that when Douglas Ratchford takes a subspace into itself, this new algorithm is going to do the same thing. And because of that, you can very, very easily prove this, which is that if you have two lines in Rn, this new algorithm will solve this problem in a single step every single time. So there's my update. It's always where the two lines intersect. And again, this is true in Rn, not just in R2, although of course in Rn, it finds a fixed point. It won't necessarily be feasible, but it allows immediate recovery of the solution. And it's actually very easy to prove this because from Min and Matt's work, you know that this Lyapunov function is just a spherical function. It's perfectly symmetric. So all of these gradient descent trajectories intersect only in the fixed point set. And as soon as you notice that, you're just done. It's basically a free result. And so given that characterization, it actually, you could think about both of these algorithms as algorithms that return you the minimizers of these spherical surrogates for these Lyapunov functions, right? They match in terms of their gradients in some sense on this restricted affine subspace defined by these respective triangles. But what's critical here is that for this circumcentered reflection method to have this property, you need to assume a whole lot of structure, or at least so far, a whole lot of structure has been assumed in order to have this proof. And of course, we already saw it doesn't work for basis pursuit, which is a non-feasibility problem. But for this algorithm on the right, the only assumption you need in order to prove this characterization is that you have a Lyapunov function and that it has this tangency condition that's in both Benoit's and Min and Matt's papers. And so for this reason, I would think that this should work, this one on the right should work for the basis pursuit problem. So let's see how it does. So here's our ADMM iterates, here's our dual, Douglas Ratchford. And so I take 3 Douglas Ratchford points, Y3, Y4, and Y5. From them, I build our triangle as before. And let's see how well we did. So here's our centering update. Here's a step of regular, continuing with regular updates. So we did better than 1, did better than 2, did better than 3, 4, 5, 6, 7, at least better than 8. I can't zoom in any further, but you can see we did pretty well. That's a pretty good approximation for the center of this. And I'll just point one more thing out to you that is kind of important while we're on this slide, which is you want to be careful not to do this too early, because you could, here we go. You can see the center isn't always good if you're not actually in the spiral yet. And so one thing you can do if you're actually using this for a real world problem is to include an objective function check, which really doesn't cost much. Okay, how am I doing on time?
Yeah, that's 2 minutes, maybe.
Perfect.
Yeah, 2 minutes. Yeah.
Perfect. So once you have this notion of using spherical surrogates, you could come to a more general idea of using elliptical surrogates or something else. And so here's just a teaser for kind of future research, future interests. And I'll show you kind of in conclusion here, walk our way back through all that we have seen, and I'll show you how this works in Rn, because working well in R2 is no guarantee things will work well in Rn. Here's a 300-dimensional basis pursuit problem. Here's regular old ADMM chugging along, and here's this new centering method with the objective function check built in. And this is a pretty typical example of what I saw. It's about 7 to 8 times faster, and if you were to read through these statistics down here, that holds up more generally, about 7 to 8 times faster when you use this centering approach. And that could be really useful for something like optimal power flow, where you have this very non-convex structure. You can see signs of spiraling. So this is something I'm interested in working on with Paul, Scott, and Lyndon. And just to sort of recap the interesting stuff that's here, this Lyapunov function characterization of CRM is really interesting, I think, because now we can use Lyapunov functions when they're known to study the behavior of circumcentered reflection method, including for these non-convex problems. So that could include things like phase retrieval, which is sort of similar to the circle and line for a number of geometric reasons. And then more interestingly, we have this new operator for which this same thing holds. We can use these Lyapunov functions to study it. But this new operator doesn't care about reflections, so we could use it. We can use this on. It doesn't matter whether it's Fista or DR or Nesterov or anything that's spiraling. We don't even need to know the subproblems. It could be a black box. It satisfies these Lyapunov functions with really few properties, and again, that's connected to the fact that we don't use the reflections. Doesn't rely on convexity, so it's a good candidate for OPF. And some more kind of general things, some takeaways from this, if you don't work in this area, are tools like Cinderella are great for just sort of seeing and observing patterns, right? All the results in this paper are a lot harder to prove than they are to see, but they're very easy to see, right? You code it up and it just jumps off the screen at you. Second sort of big picture lesson is that excursions into the weeds, looking at problems with highly specific structure like circles and lines, those can be really great. A whole lot of interesting things have come out of John's and Braley's journey into this really specific problem, including, Fran's and Ruben's new method for finding proximity operators. And sort of the last sort of point that I would emphasize is look for connections between things that seem like they might be totally unrelated. Like I wouldn't expect there to be this relationship between circumcentering reflections and Lyapunov functions, but as soon as you plot them together, it just jumps right off the page at you. So hopefully somebody found some of that interesting, and I'm happy to answer your questions.
Okay, thank you, Scott. And yeah, any questions from our audience? I mean, the graph are very impressive. I mean, you are using a very nice, graphing, interface to find ideas to explain this. So what kind of software you are using to draw this stuff?
Yeah, the dynamical geometry tool, that was Cinderella. So this was in Cinderella, which is, you can download at cinderella.de.
Okay. And, Cinderella, yeah, that's right. Yeah, very good. Yeah. Mm-hmm. Okay, so. And
then the high dimensional stuff was done in MATLAB. So that's
yeah. Okay. Yeah. So any other questions? And,
yeah, I have a question for Scott.
Yeah.
So Scott, if I remember correctly, when you have 3 points that are collinear, I think that the circumcentering operation is not well defined. Is that right?
Mostly right. Yeah. If you have 3 points, and slide 6.
So my question with that is then, so how do you deal with this situation then?
I just have a little check built into the routine that checks if they're collinear before applying this. I'll point out if they're collinear, but 2 of them are equal, then it's still well defined. It's just the midpoint. But it's if they're distinct and collinear that it's a problem. And if they're distinct and collinear, you can just have some kind of a threshold where you decide, okay, that's close enough, but I'll call it distinct and collinear. And then, if it is that, then I just compute a regular update. That's the way that it's handled in the, yeah. It happens very, very rarely. In all of my results, I don't think I ever saw it happen, which isn't too big of a surprise for the basis pursuit because it just tends to start spiraling pretty early. So.
Okay, I see. So kind of like a hybrid.
Yeah. Well, and I'm interested actually. I'm very interested in what you're able to come up with as far as training a proximity operator based on Douglas Ratchford iterates and shadows. Because for a problem like optimal power flow, right, you get these shadows for free as you're computing ADMM. In a sense, you get these Douglas Ratchford iterates for free because they can be reconstructed from the shadows at low cost. And so when this prox operator is the trickiest part in all of this, because if you can approximate it somehow as you can for basis pursuit, or you just know it directly, you're good. But on a more complicated problem, this is an interesting part of how you decide what to do.
Okay, so yeah, it's nice. Thank you